Hello again. So in this video, I'll briefly go over the pumping lemma for regular languages and how to use it to show the languages that are not regular. So the pumping lemma is actually, it gives us a property that regular languages satisfy. But even though it kind of gives us a property of regular languages, we are going to use it to show languages are not regular. And the reason is, if you know the regular languages have this property, all you need to show is that, your given target language does not have the property, and that's enough to show that it's not regular. Okay, so the pumping lemma, So it says that if a language A is regular, then there exists, this symbol means exists, there exists an integer n, the minimum such n is called the pumping length. So that this n is sometimes called the pumping length. Such that for any string of length at least n, so we can write for any such string, we can write w equals x, y, z. Okay, so these are, we decompose w into a concatenation of three strings x, y, z, with y bigger than 0. The length of y is bigger than 0. Y is not empty, and x, y together. So y basically occurs within the first n symbols of w. Okay, so the string y is going to be the key part of this composition, x, y, z. And so the string y is going to be non-empty, and it's going to occur basically within the first n symbols of w. And then the key property is such that for all I in n, x, y, i, z is also in A. Okay. Essentially what we're doing is we're saying for any string w in the language that's long enough, the length at least n, there is a special string inside of it, a special string, substring y of w, that occurs within the first n symbols of w. Okay, so it doesn't occur too far out, and it's not empty, such that if we were to repeat this string, so if we were to duplicate it, the resulting string, the resulting modification of w is still in A. Okay, so this is a property that regular languages satisfy. And the reason regular languages satisfy this property is because regular languages have a DFA. So if A is a regular language, then A has a DFA. Okay, and if A has a DFA, I mean, just let's do a little proof sketch for why the pumping lemma holds. So A has some DFA, who knows what it looks like? Okay, it's whatever. It's you can see a 0, you go there, see a 1, you go there. Sometimes you go to an accept state. Maybe the state is also accept. Anyway, so you have some DFA. We have some diagram for it. One key property of DFAs is that they're finite. I mean, it's right in the name. It's a deterministic finite automata. The F stands for finite. So the number of states here is going to be finite. And that means that if you take, let's say there's n states, if you take a string w that's length longer than n, or like, let's say there's n minus 1 states. So if you take a string w of length at least n, then there'll be some state that has been entered twice, just by the pigeonhole principle. Some state must be visited twice. Okay, in fact, I think it's true even if you had n states, because you start at one state. So you visit n others, you must visit some state at least twice. Okay, so never mind. Even if you have n states, if you have a string of length at least n, you will have visited some state twice. Okay, and so let's say when you read the string w, then this state over here, that state there, let's say you visit it twice, okay, when you read w, and this is a DFA, right? So at some point you enter it, maybe through here, and then you go do some other junk, you take another path, and then eventually you enter it again. Okay, so there's a sequence of symbols and that you read that as part of reading W. So as part of running the DFA in W, there's some sequence of symbols that starts from this state. And after reading that sequence of symbols, you still end up at this state. Okay, so X is going to be all the symbols you read to get to the state the first time, starting from the initial state. So X is the symbols you read until you get to the state for the first time. And then Y is going to be the sequence of symbols you read between getting to the state for the first time and getting to the state the second time. So reading Y starting from this state gets us back to the same state. Okay, and then Z is going to be the rest of W. Okay, and that's how we get this X, Y, Z. And so now, because reading Y just gets you back to the same state, if we didn't read Y at all, if we just took the strings xz, then the behavior of this DFA on xz will still get us to the same final state. So, we've sort of omitted the part of W where we were at this state and then we took some complicated detour and then we ended up back at this state. So in the string xz, we just skipped over that part and then just keep going, to the string z that gets us from this from the state to some accept state. Okay, so again, when reading W, we split our path into three components. There's the first path where we get to this first state, to the state in the first time. There's the second part of the path where we go from this state, do something, and then get back to the state. That's part 2 of the path. That's the part where we read Y. And then the final part of the path is where we go from there to an accept state. Okay, that's Z. So in XZ, we just omit the middle part, but we still get to the same accept state in the end. So XZ must be in A. And also XYZ is in A because we said W is in A. And also XY squared Z is in A because that just means that we duplicate the part where we do the detour. Like instead of doing the detour once where we return to the state, we now return to the state multiple times, just repeat the same detour again and again and again, in this case twice. And really any number of times, as long as it's a finite number of times, we will get a string that's still in A because that string still leads us to an accept state at the end of the day. Okay, so X, Y to Z, I is in A, and this is true for all I, including I equals 0. Okay, that's the pumping lemma. This is true for any regular language. So for any regular language, this property holds for all W in the language. Okay, so that's at least this long, where n is the pumping length. So again, for any regular language, there exists some pumping length, and it's going to be at most the number of states in the DFA for the language. Okay, it could be less. There's going to be some pumping length n, such that for all strings in the language that are longer than the pumping length, we have this decomposition of the string into 3 pieces, where the middle piece is non-empty and occurs within n symbols of the beginning, such that we have this pumping property where we can pump Y, repeat Y multiple times by, this is called kind of pumping it, and we get these other strings, all of which are in A. Okay, this is the pumping lemma. Okay, so we can use the pumping lemma to show languages are not regular. And the way we do this is by saying, okay, the language does not satisfy the pumping lemma, and therefore it cannot be regular because every regular language does satisfy the pumping lemma. So for example, let's suppose that our language A is a set of all strings of the form 0 to the n, 1 to the n, such that n is an n. Okay, so this is it has the empty string and then 0, 1, 0, 0, 1, 1, 0, 0, 0, 1, 1, 1, and so on. Okay, so let's so suppose by contradiction that A is regular. Okay, then by the pumping lemma, so we can get pumping length. So there's some pumping length n for A. So the pumping lemma gives us the existence of a pumping length n. Now we get to pick W. We get to say, okay, the pumping lemma gives us a guarantee for all W in A, right? So the pumping lemma gives us a guarantee for all W. We're trying to contradict it. So we get to pick any W that's going to contradict it. And we can pick W as a function of n. Okay, so what we're going to do is we're going to pick the string W in a way that depends on the pumping length n. In this case, let's pick, so let's pick W equals 0 to the n, 1 to the n, where n is pumping length. And again, remember, A is not going to have a pumping length in real life, because in real life, A is not going to be regular. But we are assuming by contradiction that A was regular. And under that assumption, A must have some pumping length n. And so let W be 0 to the n, 1 to the n for that n. Okay, and that's we assume by contradiction that that n exists, basically, by assuming that A is regular. Okay, so then we pick this W. Okay, so pumping lemma. So the pumping lemma says that W can be written x, y, z with x, y less than n and y greater than 0. So this means that because of this property that x, y is less than n, we know that y must be all 0. So y must be 0 to the j for some j that's it's j can't be 0, y can't be n, the empty string, and j can't be longer than n. So j is something in this range. Okay, so y is the string 0 to the j for some j there. Okay, so then that means that, so W, remember that W is x, y, z, right? So then x is an all 0 string, y is 0 to the j, and so this is x 0 to the j z, right? Where j is not 0. Okay, so then the pumping lemma says, so the pumping lemma, it then says that that x 0, so that xy squared z is in A, right? So basically it's saying that x 0 to the 2j z is in A. Okay, but this is saying that basically that 0 to the n plus j, 1 to the n is in A. But j was not 0, j was bigger than 0, so this is a contradiction. This is a contradiction by the definition of A. The definition of A is that A only has 0 to the n, 1 to the n. And here we have 0 to the n plus j, 1 to the n. Okay, that's not in A, so it's a contradiction. So therefore, A cannot be regular. Okay, so this is how we use the pumping lemma to show that a language is not regular. In this case, the language 0 to the n, 1 to the n. Okay. So there's other examples in the notes. The idea is that always we assume a contradiction that A is regular. Therefore, the pumping lemma gives us a pumping length. Then we pick a string W that depends on the pumping length. And generally, the string W is going to be, well, it has to be in A. Okay, so we're going to pick W to be in A, but we're going to want to pick W to be kind of just barely in A. So in general, like if you had an option of which W to pick, you want, first of all, you want to pick W. So it's such as its length depends on n, the pumping length. So especially if you can make sure the first n symbols are all 0 or all something nice, that will help a lot. Like if you have control over what the first n symbols are, that will help because the string y that's going to be pumped is guaranteed to be within the first n symbols. So it's going to be nice if you can guarantee that the first n symbols are all zeros, for example. But then after that, you want the string that you're picking to be kind of an edge case. It is an A, but any but just barely, for example. So let's maybe do another example. So if you had the language B and this was 0 to the n, 1 to the m, such that m is at least n. So here, we can prove that B is not regular. We'll do the same thing. So suppose B was reg, pumping lem gives n. So this is the pumping length. So the pumping lemma gives us a pumping length. We pick W, and in this case, we will put n zeros in W because we want to have control over what the string y will be. We want it to be all zeros. That's easier to handle. So we will pick 0 to the n first, and then we will pick m to also be n. So we will pick 0 to the n, 1 to the n again. And the reason is we could pick any m that's larger than n, but the most edge case, the case that's closest to not being in B, the string that's least comfortably in B, sort of, is going to be 0 to the n, 1 to the n. The string, we could have picked 0 to the n, 1 to the n plus 2, for example, but that's kind of 2 more ones than was necessary. So this string is kind of less of an edge case than the other one. The string 0 to the n, 1 to the n is a bit more of an edge case, I guess. So you should always pick these kind of edge case strings that are in B. This is in B, but just barely, sort of. If you decrease the number of ones even by 1, then it won't be. Or if you increase the number of zeros by 1, then it won't be. So it helps. Usually it helps to kind of try to pick edge cases. It's not always necessary. Okay, so we will pick this string W. Then the pumping lemma, it gives us the decomposition W equals x, y, z with x, y less than n. So y equals 0 to the j, and then j is greater than 1. Okay. And then pumping lemma says, that x, y squared z is in B. Okay, but x, y squared z is equal to 0 to the n plus j, 1 to the n, which is not in B. Contradiction. Okay, so here's another example. What if instead of m bigger than or equal to n, we wanted to put m smaller than or equal to n? Okay, so we flip now there's more ones than zeros. So again, we suppose that B was regular. We let n be the pumping length. We pick W equals 0 to the n, 1 to the n. Same thing. The pumping lemma still gives us this. Okay, everything is the same. But now, now this string, this last step is wrong. So this last step, you see how we said 0 to the n plus j, 1 to the n is not in B. Actually, now it is in B, right? So now that is in B, right? So we don't get a contradiction. Okay, so we failed to get the contradiction. We failed to use the pumping lemma. And how would we handle this case? The answer is, the trick is, remember this, the pumping lemma allows us to pump, it actually says that x, y to the I, z is in B for all I. Okay, and we took I equals 2, but let's not take I equals 2. In fact, what we want to do is take I equals 0. So we'll take I equals 0 here. So then pumping lemma says, when we take I equals 0, then pumping lemma says that x, z is in B. Okay, but actually x, z is equal to 0 to the n minus j, 1 to the n. Okay, because we deleted j zeros. And this is not in B now, because it has fewer zeros than ones, and we wanted more zeros than ones, or at least as many zeros as ones. So this is a contradiction. Okay, so don't forget that you can apply the pumping lemma with I equals 0 as well. You can pick any I that you want, actually. So pumping lemma can be viewed as like this game with against the pumping lemma, I guess. The pumping lemma first gives you n, then you pick W, then pumping lemma gives you x, y, z, then you pick I, right? And so in the end, your goal is to show that the pumped string x, y to the I, z is not in the language. Okay. So that's what I have for that. Now, remember, the pumping lemma is not the only way to show that a language is not regular. Another way that's very useful is closure properties. So regular languages satisfy closure properties. So you can kind of assume by contradiction that a language was regular, and use closure properties to conclude another language is regular, and get a contradiction because that other language is clearly not regular. So here's a common example. A common example is to intersect with a regular language. So let A be the set of all strings x in 0, 1, star, such that this is the number of zeros in x is equal to the number of ones in x. Okay, this is this notation denotes the number of zeros in x and the number of ones in x. So okay, so this is the language A. And then so we could use the pumping lemma on this, but we can also just use closure properties. So we can say, suppose A was regular. Okay, then A intersect the language of the language 0 star 1 star would be regular. So let's just say is also regular. Okay, so this is the language of the regular expression 0 star 1 star. So this language, note that L of 0 star 1 star. What is this language? It's the language of all strings of the form 0 to the n, 1 to the m, such that n and m are positive, non-negative integers. Okay, so it's this language of any number of zeros followed by any number of ones, and they don't have to be the same number of zeros and ones. Okay, so the intersection of A with this language is actually, A intersect L of 0 star 1 star is actually the language 0 to the n, 1 to the n, such that n is an n. That's because here L has a sequence of zeros followed by a sequence of ones, and A has all the strings that have the same number of zeros and the same number of ones. So the strings that have both properties are the strings 0 to the n, 1 to the n. Okay. Yet we showed this is not regular. Contradiction. Okay, so note that we used here the closure of regular languages under intersection. This is one of the most useful properties for showing that language is not regular. So one of the most useful closure properties for showing a language is not regular is the intersection property, to intersect with a regular language to kind of simplify the language A. So language A was somewhat complicated. It has a lot of different types of strings. It had A, for example, had the string 0, 1, 0, 1 in it. But when we intersect it with this regular language, then it becomes simpler. It just becomes the language 0 to the n, 1 to the n, okay, which is easier to show is not regular. In fact, we already showed it. Okay, so this is another useful way to show that a language is not regular. Here we showed A is not regular only by appealing to this language not being regular, which we've already seen, plus closure properties, the closure of regular languages under intersection. Okay. All right, so those are the two main ways that of how to show a language is not regular. We will see another one in lecture 7. There'll be kind of yet another third way of showing that languages are not regular.